Today we are going to talk about features. This is the next lecture we have in this course. And the outline for this lecture will be, first we will go through some of the basics of features, what features are and why we really need these features. Some of these aspects we have already covered in some of the past lectures, but I will try to briefly touch upon those. Then we will look into key points which are actually useful to extract some of these features. And then we will try to cover two classical approaches to extract features from images. The first one is histogram of oriented gradients. It's a very popular algorithm if you have to extract features from images. And the second one is SIFT features. It's called scale invariant feature transform. So we're going to cover these two algorithms for feature extraction in classical category. And in one of the later lecture after this, we'll see like how we can actually extract these features from, again, images using deep learning approaches. Okay, so let's start. The first segment is we'll briefly cover the basics. And as I said, most of this we have already covered in the past. So I will try to quickly go over these. Now, the question is, what exactly is a feature? So if you think about this in computer vision, what we want is we will have some kind of visual information, or you can say like some data point. It could be an image, it could be like some video, or it could be like any other, like it could be like grayscale image or any other form of input, right? Which you have to analyze or which you have to use to make some kind of predictions. So given that input sample, what you have to do is, given a task, you have to perform that task, right? If it's classification, you will have to say, okay, which class category is present in this image. So we'll have different variations of problems. So to be able to successfully do that, to let's say do even classification, you need to represent that data sample in a compressed format. And that compressed format is called feature. So it won't be like the complete image itself. It will be like some kind of compressed format, which has like sufficient amount of information so that you can solve like a downstream task. Okay, for example, classification, those features will allow you to say, okay, which class category is present in this input image. It could be image, it could be in video. Okay, so those are called features, and these features could be handcrafted. So for example, if I'm saying we are trying to go through those classical approaches, so those approaches are kind of classical algorithms, and you can say like you are extracting handcrafted features, or these features could be learned. For example, when you train your neural networks, you are training that network on large amount of those data points, right? So whatever feature you extract, it's not handcrafted. You didn't design those features. Those kernels which were used to extract those features will be learned, right? So those are called learned features. Okay, so and at the end, we just need a function which will take that image as input and give you these set of features. And it depends like whether that function is like something which you have designed by hand or the function is something like which you have learned. So that's the distinction between these two. Okay, so handcrafted features, it's also called feature engineering. You might come around with this term as well. And learned features are automatically learned. So a high-level categorization of these features, if you have to do that, you can say that some features can be global features, and the other is like local features. So looking at global features, when you're extracting these features, you have the bigger picture. For example, if you use this image to extract the features, then if you're considering the whole image, each and every pixel present in this image, and extract some meaningful features, those features will be kind of global features. Okay, so for example, like template matching, that's kind of global feature because you are considering the whole image when you perform the matching, right? Even though you are performing point-wise matching, but you use the whole image at once. And similarly, we are going to go through a histogram of gradient features. You can consider them as, and again, when there are different variations, HOG you can also use as local features. But when we are doing image matching, you will say, okay, because you're extracting these features from all over the image, these features will have the global picture. So they are considered as global features. The second variation, as I said, local features. So before going there, we have something intermediate, which you can say like region-based features. And the idea is, in this case, you're not looking at the full image. So you don't have the bigger picture. You're just looking at a small region in that image. For example, this blue bounding box. Okay, and if you extract feature from this small region, you can say that these are region-based features. So if you think about like when you were doing filtering using some kernel, right? You can consider this as like as a kernel as well, a big kernel, which is operating on all these pixel values. So that could have been like a region-based feature extractor for you. And the other extreme is local features. And the idea is you are just describing one pixel or just the vicinity of that pixel. Okay. So you don't have the bigger picture in this case. So the idea is at a high level, if you think about this, if we are looking at global features, then the global picture here is like you have a blue sky, you have like these huge mountains, you have like snow all over these mountains, right? So that kind of at a conceptual level. So global features should try to capture those aspects. Going into region-based features, the idea should be like they should focus on a very small region. For example, in this patch, whether you can say, okay, whether sky is present or not, or what kind of peak is this? Is it sharp? Is it flat? Right? So that mid-level range. And if you go to the other extreme, local features, it should be like, okay, what is the color of that pixel? Or what kind of edges, like what's the orientation of edge in this particular pixel location? So those are like the other extreme of feature extraction. Okay. Now, so that was just high-level categorization of this. Now, the question is, once we have these features, why exactly we need to extract these features from images? And once we have these features, what should we do about these features, right? So as I said earlier, once you have this compact representation of your data point, then you can use these features to solve any task. It could be detection, it could be recognition. You can use these features for tracking and a lot of other computer vision applications. Okay, so then the question is, if like a single set of features can actually solve all these tasks, why do we need like different type of features? And the reason is simple, because different problem domains might have different requirements, right? And different features might be extracting different kind of information. So one simple example I can give you is like, for example, if a feature is actually looking at the colors which are present in your input image, and whatever task you have, if the task depends on the color, so that might require different kind of feature, right? For example, if you have a task like you have images of apples and you want to build like an automatic system which tries to figure out automatically whether you have a green apple or a red apple, right? Then you really don't need like a lot of like detailed features about that image. Just the color information will be sufficient. So in that case, you might need different kind of features, as against like if you have a problem which says that, okay, given an image, you have to identify whether there is apple present in the image or not. So in that case, color might be useful, because you might not have like a very odd colored apple, right? So you won't see like maybe pink apple or purple apple. So color is important there, but again, the shape of that object is also important, which will help you in recognizing whether apple is present or not. So again, depending upon the task, the requirement of these features will change, and that's why we need different kind of features. So let's quickly go through some of the applications where we can utilize these features. So if I give you this image, right, and for you, I think as a human, it's pretty easy. Like you can see, okay, seems like a pentagon, right? And you have like all these roads, you have bridges, you can identify the river, right? So you have some kind of representation like inside your mind, which you construct while you're analyzing this image. And based on your prior experiences, what you have seen in your past, you will be able to make inferences about different aspects of this image. Okay, so matching is one interesting application where the goal is, let's say if I give you just like a small patch of this image, and this patch could be maybe coming from the same image, or this patch could be like a different view altogether. For example, in this case, I have this top view of this building, right? And you can see like this is kind of the image on the bigger image on the right. It's not directly from the top, it's kind of an oblique view. And that's, I mean, you can't just do like a point-wise matching between this patch and this building over here. It won't match. But as a human, we can easily say that, okay, this seems like the same building, and we don't really understand like how we do that, but that's how that's like you can say like one great visual power we have. So now let's try to understand if we have to match this patch and try to figure out where exactly this object is present in this image. So that's called you can say patch matching or image matching. And as I said earlier, since the viewpoint is different, because this is like captured directly from the top and this is an oblique view. So even if you try to do a pixel-wise matching of these two patches, it's not going to work. So viewpoint is one reason. The other reason is you can see like the contrast or the color values, right? This seems like kind of washed out, or you can say it could be even grayscale here, but this is like is very colorful image. So even in that case, the pixel values won't match because the values of those pixels will be different. So in that case, features are actually important. If you take this patch, extract feature, then that feature will actually capture like what structure this patch has, right? This pentagon shape. So all different shapes will be captured in that compressed format. And again, if you try to extract the same set of features from patches inside this image, so the idea is that feature representation will be very close for this patch and the features which are extracted from this particular patch, if it's a good feature. Okay, so then that's how you can actually perform this image matching, or you can say patch matching, to figure out where objects are present in your big image. Again, another interesting application of matching, even in this case, you can see like there is like a lot of difference between the kind of the coloring you have, right? Of course, these are like the same objects, it's the same location, but the viewpoint is different. But as a human, you can easily actually match like each statue you can easily match, you can locate. But for a computer vision algorithm, it's a very challenging task. And that's why we have to extract features compressed format, which can save like the structural information which is present in this image. And instead of doing pixel-wise match, we match those features. Okay, so this again is a very interesting application of features. And I think I have a very cool demo for this as well. The idea here is if you have lots of images captured for a location. Okay, so this is a monument in Rome, and these pyramids here are actually showing you the locations, the GPS location from where like images were captured of this monument. And the cone is actually showing you the direction, the viewpoint. Okay, so all these images, and these are just some samples from that set. Now, what you can do is if you have this kind of information, you can extract features from these images, and you can try to actually match those features across images to figure out whether there is some overlap between images, right? And so this is called structure from motion. And given this like set of images, you can actually try to reconstruct this monument. And this is a real world example. I mean, this was done using computer vision algorithm, given all these set of images. So this is pretty cool. Okay, so image matching is like a very key component in this algorithm. The other interesting application is panorama stitching, and I think most of you might have this in your camera itself. So when you are capturing the panorama, so the application will ask you to actually move your phone, right? But what's happening behind the scene is the camera is actually capturing all those images in sequence, and then it's trying to actually match those images which are captured in sequence on top of each other. And this feature extraction of feature matching is being performed on the background so that your image is actually very smooth once it's captured. Because how hard you try, I mean, you will have some shake in your hand, right, when you move your camera. So all of that is actually taken into account when we perform feature matching and when we try to stitch those images together. Okay. Now, another interesting example, I think this is really motivating. And this is showing, given a video, of course, as a human, we can watch the video and we can infer a lot of things about it, like what action is happening or what different objects are present in the video. So a lot of those things. But again, as images, it's very challenging to actually do inference on videos, because first of all, like, it's very complicated, right? It's more complex than video. We have this additional dimension of time. Okay, so let me show you like one very simple representation of videos. And so, for example, this is called like point light displays. And what we do here is, let's say we have a human, a person performing some action. We just identify the joint angles, okay? The joint angles of like the human skeleton. And these white dots on the right are exactly showing that. So this was like a very dense image, right? You have this person, so a lot of information here. But what all we are interested in is just these joint angles. And you can think about like this image will require a lot of memory to save these pixel values. But if you just store these joint angles, it's like just 2 points, like X and Y points for each joint angle. So even if you're storing all the 25 joint angles of human skeleton, you only need 50 numbers. Okay, so that's pretty compressed format as if you compare that with the original image. And this is like another example. Now let's have a look like how this is pretty useful. And of course you can use this for like a lot of other applications. I will just show you like for action recognition. And of course you can use for facial recognition, sign language, and all of those. Of course, the key points will be different there. Okay, so now look at this. So in this case, I'm not showing you any colors, right? It's just black and white image. And what I have done is I've just tried to connect like those joint angles. So it's a very compressed format. And if you look at this, you can say that, okay, a person is walking. It's pretty easy for us. If I compress it further, let's say I don't show you like the connected joint angles. I show you just the joints. Okay, so you can, it's hard. You might not be able to say what's happening there. But if you have some kind of prior knowledge that, okay, you are looking at a person who is walking, then you can guess, okay, it seems like a person is walking. And we can make it denser. And then it becomes more, it's easier, right, as compared to the center one. Now, as a human as well, like it's easy for us, and it's interesting because it's actually solving two purposes. The first is it's actually compressing the amount of memory you require to save your data, right? And the second is it's like a very compressed format of your action, what is happening in your input video. And it will be a lot easier for your computer vision algorithm to determine like what action is happening in this scene, as compared to by looking at like the full RGB image. Okay, so this is one example of how you can represent or how you can extract features from your videos. And it's a very compressed format. All right, so that was just some motivation to show you some applications and some use cases of why features are required. Now, let's try to cover some points like what kind of features we want to extract and what should be like some good characteristics of these features. So the first point is these features should be distinctive. So by distinctive, the idea is like if you're extracting some feature from a location in your image, it should be different from like any other feature you're extracting from the same image. Because if you don't do that, then there is kind of redundancy and it's not like a unique representation of that image. Okay, for example, like for the sky region, you can extract features from all the locations, but the features won't change, because it's kind of a flat surface, right? So all the features will be almost similar. So it's not kind of distinctive as compared to like these dots over here, which are shown. So all of these will be different because you have different kind of texture in these regions. Okay, so that's one property. The second is repeatability. And the idea here is if you have an algorithm which can extract features from a given image, so no matter how many times you try, 1 time, 2 times, 3 times, 1,000 times, the extracted features should not change. Okay, so that's called repeatability, because if the extracted features are changing with every iteration, then they are not consistent, they're not useful, right? So they have to be consistent. And the third characteristic is they should be compact and they should be like efficient to extract. So by compact, it means that if you're extracting features from, let's say, a video, it should require less memory than the actual video. Otherwise, you can just save that video itself, right? So for example, the example I showed you earlier, when we were extracting those key points, it was a compressed format. Okay. And it's not just about saving memory, it's also about the generalization capability of those features. And we'll talk about some of those things later on. The second part is efficiency. It should be efficient when you are running that algorithm to extract features. Okay. Because it could be like you have a very, very nice algorithm, very perfect algorithm, but if it takes, let's say, 2 years to extract features from one image, it's useless. We don't need that, right? It doesn't matter how perfect that is. So in terms of computational cost, it should be efficient. And again, that varies from application to application. If you have like some kind of real-time application, then it should be like pretty fast, right, in nanoseconds or in milliseconds. So, but it should be efficient. Okay, so this I think we just covered. This is also fine. So let's continue on like this features lecture. The next segment is key points. Now, if I show you this image and I ask you like, what are different interesting points in this image? Okay, so you will say that, okay, I can see maybe a road is there, there is a bridge. And I mean, I can even ask you like your very interesting question. If you are at this location and you want to meet your friend, forget about like all these mobile phones, location sharing and everything. Consider like old days when you didn't have mobile phones. And both you and your friend are like familiar with this location, then you might, and you want to meet your friend. Then what you will say, okay, I mean, at this particular time, let's meet at some location. And that location, which you will say, that would be something, it could be like maybe corner of the bridge, or you can say maybe close to like some tree which you both recognize. So it will be some interesting point, right, which you can easily identify in that location or in that spot. It could be some shop there, some building. So if you think about this, how it works is that location should be like distinctive. There should be no confusion. For example, if there are two bridges in this road, you will never ask your friend to, okay, let's meet on the bridge. Your friend will not know which bridge. Okay, so it should be distinct. And that's the whole idea about key points and interesting points. That's how like we want our algorithms to also operate. We want those algorithms to actually identify those key locations or key points and use them to perform whatever downstream task you have. Okay, so that's like a high-level intuition. So now let's describe what these interest points are. And so it will have some properties. For example, it should have like some kind of unique texture, right? So, and again, it's kind of arguable like what interest point is. And there are a lot of different variations. We'll just try to cover some of those. Because this has to be very concrete, what we can do is we can define interest point as when like certain boundaries are actually changing abruptly. Okay, so it could be this point here. And if you try to think about what's so special about this point, which is not like in this point over here, let's say. So this point is kind of it's boring point, I mean, nothing is changing, right? It's just a flat surface. So it doesn't matter whether you are at this pixel location or this pixel location or this pixel location, all are same. Okay, so that's why it's boring point. But if you look at this location, this point is pretty unique. I mean, I will say there is no other point in this surface which is as unique as this. Because what's happening here is, you can see like this whole surface is actually meeting with like these two slopey surfaces. And then again, you have this flat surface on the top. So this is kind of, you can say, a corner or like a point of intersection of different surfaces where different segments are meeting. And I can easily call this like a very interesting point. Okay, so those are the points which we are looking for. And again, this is also interesting. You can see like different surfaces are actually, you can see how different edges are actually intersecting. In this case, we have one more surface actually meeting at this point. So we call such points as interest points, and let's try to like make it more concise. Now, if you look at this image, this is a grayscale image, and there are different shapes present here. Okay, so let's try to find out like which points are actually interesting and which are boring. And the interesting points will be our key points. Now, if I pick any point like in this dark region, I mean, I think it's not interesting, it's boring because there are a lot of such points. There's nothing unique about that point. But if you carefully look at the points like which are marked in these red dots over here, they do have some kind of unique property. Something interesting is going on like around that region. Okay, for example, all these red dots on the left, you can see like it's kind of corner of these squares or these blocks. Right. Similarly, you have this this shape here. These points are interesting because different line segments are actually meeting there. And you can find like different structure at these points. Okay, so in a crude way, we look for these kind of points and we call these interest points. And these are like some sample examples. Of course, you will not have like these simple interest points in real world images. It will be entirely different, more complicated than this. But you get like the basic idea what we are looking for. Okay, where different like edges or different surfaces are meeting. Now let's look at like a real image. And again, this is a grayscale image. And if you try to draw the analogy, again, you can see we don't have any interesting point in the sky because it's kind of boring. Nothing is changing there. Same with the roof. If roof had like some kind of texture, it might have been interesting. But right now we don't have any interest points here. But again, on the surface, on the ground, we don't have anything. You can see like on top of the car, we have several interesting points because different lines or different segments are meeting there. Right? We can see something interesting going on. Similarly, on the window, and a lot of interesting points on the tree because there are a lot of like short edges. Okay. So interest points, the idea is, again, that was like a very crude definition of interest points. We will try to formalize that in next couple of slides. But what we want is we want to detect such interest points in your input images. Okay, so we want to detect all these interest points. We don't want to miss anything. If you want to represent your image well using some set of features, we should not detect like any false interest points. For example, if a location is boring, we don't care about that boring location. These should be well localized, which means we should exactly know where that interest point is. Okay, and these interest points should be robust against any kind of noise you might have in your input image. And this property you have seen like when you're trying to do edge detection as well. And of course, it should be like efficient to detect these interest points. We can't take like years or centuries or decades to detect these. Even minutes, I think it's computationally expensive. Okay, so one possible approach is corner detection. What we can do is, if we just try to detect corners in your image, they can be represented as interest points. And what we do is we try to make use of image derivatives. I think now you are well familiar with how to compute image derivatives and what they represent. So we'll try to make use of those. And we'll also try to extract like this boundary to be able to do corner detection. Okay, so let's try to understand like some of the key properties which we want when we perform these key point extraction. Now we have this object. So we have image number 1 on the left, and we have image number 2 on the right. So you can clearly see these like correspond to the same object. Okay, it's just like rotated. The scale is slightly bigger. Now the first property I think which we discussed was repeatable. We want these key points to be extracted exactly the same way like it was done in the first round. So it should not change. Okay, and we want these points to be distinctive. And so that's one key property of these key points. Because if you choose like these dark regions here as key points, then it's kind of not distinctive. There are a lot of these dark regions and you cannot really tell, okay, which one is which. So here I'm showing you some key points which are present in this image on the left and the corresponding key points on the right. Okay. So if your algorithm can actually detect these key points in this image, and it's like able to repeat the same thing on a different set of a different image, which is again of the same object, and it can identify the same set of key points, then you can use those key points to actually perform image matching, right? Because those key points, if they are matching, then you say, okay, it's the same image, even though the image is rotated. Right, so let's try to understand how we can actually use these key points for key point matching. First step, it's fine, you detect these key points. So don't worry about how these were detected. We'll cover some algorithms for that. For now, just assume that, okay, we have an algorithm which can do this. So we detect key points in the first image, we detect key points in the second image, and these crosses are actually showing you those. Then the second point is you will define some kind of region around this key point. In this case, this is the window shown by the yellow bounding box. And you will do the same over here. And you can see that the bounding box on this image is actually slightly smaller than bounding box on the right. Okay. So then the idea is when you are detecting these key points, you should be also able to tell the scale of that key point, how big that key point is, so that your algorithm is actually scale invariant. Okay, if you enlarge your image or you have a bigger object, which is the same object, then you should be able to match these key points. Okay, so then what you do is you extract features from this patch. So let's say if you just focus on this, it will look something like this, right? And if you extract from this location, it will look something like this because it's slightly bigger. The scale was different. And the third thing which you will need is some kind of a rotation variable, which will tell you, okay, what is the orientation of this object? And you will use that orientation to fix the alignment of this patch. Okay, so you rotate that, and now you can see that, okay, these patches look exactly the same, which means that these two different key points are actually same part or same key point in your input image. Okay. And the final step is you extract some kind of features from this patch, extract some kind of features from this patch, and you try to match those. So this is kind of, you can say, like region-based features, because you're not using the whole image. You're only using this small region over here. And if they match, then you say that, okay, key points coming from the same image. And similarly, you can do for all the other key points. And if all the key points match, you can say that, okay, these two images belong to the same object. Okay, so that's how, like, one simple, interesting application, how you can, if you have an algorithm which can detect these key points, how you can utilize those key points for image matching. Also, on a large scale, I mean, it doesn't work this way, but if you think about this, these days you have image search, right? So this algorithm can even be used for that image search, whether it's like Google image search or Bing image search. You will give like your input image, which could be this image, and then that algorithm on the backend will detect these key points on your provided image, and it will do the same for all the images like which we have in like Bing server or Google server, which will give these kind of key points, and you will follow this exact same set of steps. And then what will happen is the images which are actually very close to each other, based on these features, your Google search engine or Bing search engine will retrieve those images or show you those images. Okay. Now, let's go through like one of the corner detection algorithm. And the idea here is we'll try to find these corners where different edges are actually meeting. And this is from this very famous paper. Okay, so it's called like Harris corner detector. And let's go over like the basic idea of this algorithm. So in this algorithm, what we want to do is we want to, first of all, not look at the global picture. We'll look at small windows or small regions. And we try to find out whether in this small vicinity or this in smaller region, whether corners are present or not. And as we discussed earlier, like corners could be interesting points. And of course, not the only interesting point. There could be a lot of other different ways to define interesting points, but this is one of the variation. Right? So what it tries to do is It tries to find out these corners in small windows. And what this algorithm does, you operate on these small patches and you try to shift this patch in the image, okay, in various different directions. And the idea is, if you change the location of this patch and the intensity is actually not changing, then it's not a corner. Okay. And if the intensity is changing, intensity changing means like you're trying to match actually that patch with the image patch. If the intensity doesn't change, it's not an interesting point or it's not a corner. But if the intensity will change, it means there will be a corner. Okay, so let's go through these simple examples to understand this better. Okay, so this is your location. Now, what you can do is you can just count the intensity of all the pixels which are inside this box. Right, all of these are black pixels, so it will be 255 if you compute the average value, or you can select 0 if 0 is black. Yeah, if 0 is black. Okay, so the average intensity at this location is 0. Now, if you slightly move this towards left, towards right, or top or bottom in any direction, that intensity will still remains 0 because the pixel value is not changing, which means that your surface is kind of flat and there's no change in any direction, and it's not a corner. The other way could be, let's consider like this patch on this location. Okay, if you move your filter in top down direction, again you can see that there will be no change, right? Because the number of white pixels will not change if you move this towards the top, or if you move this towards the bottom. And similarly, the black pixels are not going to change. So the average intensity will still remains the same, although it's an edge, but it's not a corner. Okay. Now, if you put this patch on this corner right over here, then it doesn't matter like in which direction you move your patch. You will always observe a change in intensity, right? For example, if you go towards like this direction, which is left top, then you can see that number of white pixels will increase and number of black pixels will reduce, which means your intensity, average intensity, is going to increase. And if you, let's say, go towards right bottom in this direction, then again, your black pixels are going to increase, white pixels are going to reduce inside that region. So your intensity again will change, it will drop. So it doesn't matter which direction you go, your intensity is always changing. So this is a very, very clean technique, right? Very simple algorithm. And you can identify like any corners you have present in your input image. Okay, so let's see like how exactly this is done. Of course, that was like a high level idea. We need like a much more complex algorithm for that. And I will have to select this. This is like the most complex algorithm we are going to study in this course. And of course, we are not going to go into detail because this algorithm itself will take, I think, a couple of lectures if we try to do that. Okay, but I will tell you like which part you should focus on, which part you can ignore. I think that will be useful for you to go through this. So the basic step, what we can do is we can just perform template matching. And template matching you have seen a lot in this course. Okay, so the idea is you create template of these corners, something like this. Okay, so this is a template of a corner where you will see like a corner like this. And if you put this patch or this kernel on your input image, then if you will have a corner like this, it will be able to identify that because that's the pattern we are looking for. Okay. Similarly, this particular pattern template here, it will look for corners which are in this direction. Right. Similarly, you can create like other templates, like you can just keep rotating these values. And whenever you will have a matching corner, these templates will be able to match it. Okay, but this is like a very crude algorithm. And of course, we don't use this because this is like a lot of limitations as well. It is only considering like some discrete values, right? Of course, you can make it like slightly bigger and make it more smooth, but still it will be discrete. Okay, so that's fine. So the other thing is like the summation of this filter should be 0, which I think you know by now. It's kind of trying to normalize. And if you have different intensities in your input image, then you don't want them to be like different. You want the response always to be the same number to be able to identify whether there's a corner or not. All right, so that was like a very simple algorithm. Let's go through like the actual algorithm, the Harris corner detection algorithm. And before that, let's do a quick revisit of correlation. And just to refresh that, and you know this equation. To compute correlation, you have a function, you have a kernel, and you perform element-wise multiplication of these two. Okay, and that's going to give you just one number. And if the input pattern matches with the kernel, you will get a very high value. If it doesn't match, you will get a very low value. Okay, so now what we do is we try to find these corners, or you can say like interest points in your image using autocorrelation. So now let's try to understand what autocorrelation is. So you have seen correlation where you have like a input patch from your image, and then you have a kernel. So you're trying to find correlation between those two different, you can say like kernels or filters, right? Autocorrelation is you have your image and you extract the kernel from the image itself and then find correlation. So you're actually finding correlation within image. You don't need external filter. Okay, so then what will happen is if you are like at a given location in your image and if you extract like that patch, so if you apply that kernel at the same location, it will perfectly match because you extracted it from that location, right? But if you move around that kernel in the vicinity, so that's the key. So you know, not just like apply on the same location, you apply in the neighborhood, and that's how you compute this autocorrelation. Okay, so what you do is you extract this window from any location XY, and you shift that by these values U and V, which defines the neighborhood, like how far you want to go in the neighborhood. And then you just find the difference between these. Okay, so IXY is the exact location where you're interested in. And this I, X plus U, Y plus V, it represents like the neighborhood. So what you're doing is you're just finding the difference, whether the pixel intensity is actually changing in the neighborhood or not. Okay, and then you just square that value. And this is just a weighting function, which can be like, you can just ignore it. You can actually use a Gaussian weight here. And again, it has the same idea. Like if you want to pay more attention to the center location and less attention to the other locations which are far from the center. So this is like just to weight that. And you can even ignore this, so don't worry about it. Just focus on this. Okay, so now if you think about this, if at a given location in your image, if it's a flat surface and the intensity is actually not changing, what will happen? It doesn't matter like where you go in the neighborhood, the pixel intensity is not going to change. So if you compute this subtraction, it will always give you 0. Okay, which means if you are at a flat surface in your input image and you compute this autocorrelation using this equation, you are going to get 0. Okay, which means the point is not interesting. Now, what will happen if the intensity is actually changing a lot in that neighborhood? Then this value is going to get bigger. Okay, so which means that your autocorrelation value will be higher, and which will help you in determining like those interesting points. Okay, so that's like a high level intuition, and I think now I'm going to show you like some detailed maths, and you don't have to worry about it. It's doing exactly the same thing, the intuition which I explained to you, but like in a more formal way, and it's trying to actually optimize this process. Okay, so this is intensity, as I told you, like the current location where you're interested in. This is shifted in intensity, like in the neighborhood. You are taking steps U and V, and this is just a window function. Okay. And again, this window function could be like, as I said, just like a step function 0, 1, where you are paying equal attention to all the neighborhood values. It could be a Gaussian, it could be any other function. So this is not really important here. All right, so what will happen if you look at this image patch? Again, these are pixel values. So for each location, you will compute this autocorrelation. So if this is the neighborhood, this red bounding box, and then this is the center pixel location where we are interested in. What we will do is we'll compute like the intensity difference with all the other pixel values inside this region using this formula, and that's going to give you this value. Okay, so this is like you can say a response function using this autocorrelation of this input image. Okay. Now we can use that kind of autocorrelation to actually find corner detection. So let's focus on this real world image, and we'll look into 3 different cases. Okay. So we have 3 different points. One point is at this location, which is kind of like the edge of the roof. Okay. The second is over the clouds. And the third is, I think, over somewhere on the ground, over these leaves. I'm not able to actually locate that. Yeah, over here, right over here. Okay. And then we compute like this autocorrelation, the equation I showed you earlier, and these are the responses for these 3 different locations. Okay, so what's happening here? And again, these plots are just like surface plots for the same response. Okay, it's just like instead of 2D plot, you're creating a 3D plot of that. So this kind of response you will get from maybe the clouds, right? Because it's perfectly smooth and it's not changing a lot. And this kind of response you will get from the edge, which is on top of the roof. Okay, and this kind of response you will get like something from the ground. And you can see that like you have like this kind of peak over here. And this peak is something which we are interested in. So this peak will define like whether you have an interest point or not. So in a way, you can see that we have interest point here because this is kind of a peak here, right? And this is interest point, but this is not so interesting. The values are not changing a lot. Okay, so that's how you can use this autocorrelation to find corners in your input image. Now, if you think about this, what exactly you're trying to do is you're trying to compute the difference between the pixel intensity with the neighborhood, right? All the pixels like in the neighborhood. Now, if you think about like the amount of computation you require, for each location, you will have that many computational steps. Okay, and if let's say the image resolution is 600 cross 600, the total number of computations you'll have to do to get that response for an input image, it will be almost 5.2 billion operations, which is a lot. Okay, so it will be computationally expensive. And that's why we have like optimized algorithms to do that. And I will just briefly give you the intuition like how we can optimize this without going into more detail. And you don't have to worry about like if you don't understand any part of that. Okay, so before that, if you think about what exactly we were looking for, we were looking for like a strong peak, something like this. Okay, so this peak represents if a current pixel location is actually distinct from the neighborhood. And that's how we define interest points. So if you look at this, the surface, it actually looks like something like this, right? You can kind of approximate this with this bell curve here or bell surface here. Okay, so that's a quadratic surface. And now what we do is we try to approximate that using a different function. And before coming to that, we'll need, I think, Taylor series for that. And again, don't worry if you don't recall Taylor series or anything. You don't have to really understand what's going on. But if you do, I think that's really good. And I will be happy to like discuss if you're more interested in this during the office hours, but I will quickly run through this. Okay, so Taylor series, you can approximate any function using this series. And in the series, you have like different set of derivatives. Okay, so if you compute derivative at any given point, then you can compute like multiple derivatives and use them like to represent this function. For example, the series over here, we are computing derivatives at point A, and that function, the original function f, can be represented by this series over here. Okay, so you have the original function value at a. This is the first order derivative, second order derivative, third order derivative, right? And usually like the higher order derivatives actually will give you very small values. So if you have to approximate, you can actually just get rid of these higher order derivatives and maybe just use first 2 or 3 terms. Now, if you look at this simple animation, the actual function you had was exponent of x, okay, the blue curve. And the red curve is actually showing you, it's trying to approximate this function using Taylor series. And if you look at these values of n, this is like how many terms we are using. Okay, if you just use the first term, you can see it's just like a horizontal line, okay, because it's just fa, right? It's just one value. And if you take 2 terms, then we'll have to compute this first order derivative, and then you have the slope as well. So that's why the horizontal line. And as you keep including like these higher order terms, you can see that nearly, I think, n equals to 5 or 6, you're kind of very close to this function. Okay, just like very simple example here. Now, why that is important? Because now what we want to do is we don't want to compute like this pointwise difference. We want to approximate this. Okay. So how we do that? We actually compute the second moment matrix, and this is using image derivatives. So basically, this equation over here, this can be approximated by the simple matrix multiplication. And again, as I said, we don't have to worry about like how we get that approximation. It's like a long theoretical proof. But this is a way to approximate that equation. And in this one, this moment matrix here, why derivatives are important, why we're talking about derivatives, because this moment matrix is actually composed of derivatives of your input image. Okay, so this is exactly your M matrix. And these symbols are like, this is your first order derivative, a partial derivative in x direction. Again, you multiply x and y. This is the same term. And this is partial derivative in y term. All right, so now the idea is once you have this moment matrix, you can actually compute this response. And this response is like all we care about. So what we do, given an image, we just compute these partial derivatives. And we'll try to combine them to get that M matrix, which will give you the final response. And there are a lot of heuristics involved. So it's not that it was invented in a day, week, or month, or year. I think it's like research of several decades. So I don't like expect you to understand this like just in one lecture. And that's why I said, don't worry about, but just try to understand like the overall steps which are being performed like in this algorithm. Okay, so let's say this is your input image. We compute like partial derivatives. This is in x direction, and you know that how to compute this, what this means. This is basically just like edges in x direction, right? Similarly, you can compute edges in y direction. This is the xy component, and you can just multiply these two. That will give you the second part here. That part is also similar. Okay, and you can also like just multiply ix with itself. That will give you the first term over here. And if you multiply iy with itself, it will give you the fourth term. So using image derivatives, you can get the elements of this matrix. Okay, so this is like the corner algorithm. As I said, it's I think the most complex algorithm in the whole course. So the first step is you compute M matrix. Okay, M matrix, you know like what are the components, you know how like all these steps are being computed. And once you have that, then you try to compute cornerness score for each pixel location. Okay. Then a lot of heuristics involved. First of all, like how to compute cornerness. Again, we have some heuristics for that. And it's not just heuristics, like there's a lot of theoretical backing to it, again, which we will not be able to cover. And then we put like some kind of threshold on this cornerness score to determine whether that point is corner or not. Okay, so once we have done that, we will perform non-maximum suppression. You have done that earlier for edges as well. So it's exactly the same algorithm. And the idea is like, if you are saying this particular location is a corner, then you should make sure that there are no other corners in the vicinity, right? You should have like some very unique corner. And that's the whole idea about using non-maximum suppression here. And the idea of threshold is just when you don't want to detect too many corners. So that's why you need to set some kind of threshold. And the intuition is same like which you used for edge detection. You have some sort of threshold there, right? To determine like whether this is an edge or not. Okay, so let's quickly go through each of those steps. And this is your input image. You can compute like these partial derivatives, ix, iy, and you can perform blurring as well. You know that if you perform some kind of blurring or smoothing using Gaussian filter, that improves your edge detection. So that's optional, but you can do it. You can compute like the components for M. This is just ix square, iy square. So this is you're just multiplying the element wise these values of the matrices. Okay. And then you have like Gaussian filtering on top of this. This is one additional step. And then you have a equation for cornerness. And again, don't ask me like how you get this. Again, there's a long theoretical proof for this. And this also involves like eigenvectors, eigenvalues, which we briefly covered in the second lecture, right? But I think we really don't have time to talk about all that. But you have a function which actually tells you which of these points are actually corner and which are not, which will give you some kind of score, which looks like this. And the equation is exactly like this. You compute the determinant of this M matrix, the image moment, and you compute the trace, and you have some, again, one alpha parameter here. Okay. Then, as I said, you use a threshold to pick like which is corner, and then you perform non-max suppression to identify which are the peak values or which are the corners. Okay. So again, this is one of the first corner detection algorithm, or you can say key point detection algorithm. So I just wanted to talk about this because this is like gives you an idea like how it all started and how complex it was. And let's look at like some of the results. Okay, so these are the input images. You can see the lighting conditions are different. It's slightly rotated as well. This is computing the cornerness response. So after you compute the M matrix, you have that equation where you computed the determinant of M, then the trace of M, and using the parameter alpha, you get this response. Now you see that you are detecting a lot of corners, right? This is not really useful, and therefore you need a threshold. Okay, so you set a threshold and you say that, okay, only some of these are corners. And then you can see that, okay, this really needs some kind of non-maximum suppression, because in this vicinity, you can't have like all these key points. And you run that algorithm where you suppress like the neighborhood, only pick like which has the highest intensity. That will give you these key points. And you can see that the images were of the same object, right? And the lighting condition was different. The right image was slightly tilted, slightly rotated. But if you carefully look at like the key points which have been detected, I mean, they kind of match. Okay, and that's why like these key points are very powerful. These key points like plotted on the image itself. You can see, I mean, you don't have any key point on the flat surfaces, right? Only at these interesting points, which is pretty cool. You can see like this interesting shape here. You have a lot of key points on this boundary. So in a way, if you think about this, this is kind of trying to find the boundaries. Okay, so that's one use case. You can see like it's on the boundaries, right? And again, not like very flat boundaries. You can see like if, for example, these feet over here, right? It's you don't have any key points here. So if it's kind of curvature, or if like you have different edges meeting together, those kind of points you can see on the horns here, right? So those key points are actually detected. Okay, I know like that's a lot of maths there, and as I said earlier, I don't expect you to understand all of that, but at least if you can understand like these steps, how this algorithm is actually extracting key points, I expect you to understand that how you compute gradients, you know that how you're getting these matrices, this like just you use those equations, right? And I don't want you to understand like how we derive this equation. As I said, it was decades of research, which will be very difficult to cover like in just one lecture, even in this course. All right, so so we were talking about features, and so this is like I think the second or third segment of this particular lecture. And in this segment, we are going to talk about histogram of gradients. So this is also called HOG or Hawk features. And this is, I will say, like a very simple algorithm. It gives you like very powerful features, which still I think if you try to use it for like some simpler problems, it will give you very good performance, very competitive performance. And of course, I mean, you can't compare this with like the features you're going to learn using deep learning. We'll jump into that in a later lecture as well. But this is, I think, one of the algorithm which combines actually different techniques, which of course we have learned like throughout the course. And you will see like most of those techniques are being used in this algorithm. So that's actually it's actually quite interesting. Okay, and it's not a very difficult algorithm. So last lecture, I think uh, we were talking about key points, right? So that, as I said, was the most complex lecture, and this you will find like a lot easier. Okay, so let's do a quick recap and try to understand what these HOG features are based off. So edge detection, of course, you know by now, you have done an assignment as well, and you know how like to detect edges from your images. Given an input image, for example, as shown on the left here, you can have like different kind of edge detection algorithms. And on the right, it's giving you like what all edges are present in this input image. Okay, so the HOG features is actually based on this. What you will do is first you will have this input image and you will try to extract these edges. And then you will utilize these edges to construct, you can say like manually construct some kind of features. And those features will represent what is present in this input image. Okay, so one drawback, or you can say limitation, or that's also positives as well. But let's first talk about the limitation. Now, given this image, if you extract these edges, now if you think about this, like whatever color information was present in this image, that's completely lost because we are only looking at edges. Okay, so if you have a problem or a task where color is actually very important, then these kind of features will be like not be very useful because color information is completely lost. And again, HOG features are based on these edges, which means that they are not capturing color information at all. Okay, so that's, you can say like a kind of a drawback as well, or a limitation, but it could be beneficial as well for some scenarios. And those scenarios could be, let me give you like a very concrete example. For example, you are developing an application in biometrics, right? Or it could be any other application where you can say that the appearance or the color information is actually not useful. Okay, so biometrics is one, and then you can say maybe action recognition is one, right? So for example, you are doing human action recognition, and the goal is, given a video, or let's say given an image, there is some kind of pose present in this in that image, right? A person is performing, let's say it's hand waving, or it's like something else, like some hand gesture. So you can think about like if it's, let's say, gesture recognition, then color plays no role there, right? It's just like what's the orientation of your fingers or your hand. That is more important. So in that case, if we use these kind of features, which are like, let's say, edge detection, so this is already filtering out those colors. So it's beneficial because if you train a model, that model might be learning something based off color. Okay, so that you can also say is kind of a color biasness or something like that, right? So if you do this like explicitly, you ignore all the colors, then it makes easier for your model to actually learn from such kind of data. Okay, so in that sense, these kind of features can be beneficial as well. All right, so the first work where I think this HOG feature was proposed, it was back in 2005, almost like 17 years back, and they were used for human detection. And of course, these days they can use for like many other problems, for example, classification, object recognition, or anything like where you have like some kind of visual processing. But initially they were proposed for human detection. And so to be able to understand this, we'll have to do some revision of like histogram. And again, we have covered this, but let me quickly go over this, what histograms are. Given an image patch, okay, so this, in this case, it's image patch, but it could be like any, it could be like collection of numbers. right? And so given this kind of image patch, a histogram is something which is counting the frequency of these numbers. Okay. For example, in your image, let's say it's a grayscale image, the values can be between 0 and 255. Okay, so each pixel will have value ranging from 0 to 255. So if you have to draw a histogram, what that will represent is in the x-axis, you will have bins, and these bins will be the possible values. For example, grayscale, these will be 0 to 255. Okay, in the x-axis, you will have on the left, starting from 0, that will be your first bin, 1 will be second bin, and so on and so forth. You will have total of 256 bins. The y-axis over here, it's just counting how many times that particular intensity or that value of pixel actually occurred in your input image. All right, so let's look at like this very simple example. Here you can see that you have values ranging from 0 to 5, right? And that's why in the x-axis you have values like 0, 1, 2, 3, 4, 5, and then you have 6 as well. But you can see that 6 is kind of 0 because no pixel had a value of 6. Now, if you count like how many pixels has a value of 0, you can simply count that, right? 1, 2, 3, 4, 5. So it's going over like over this point, right? So it's saying that 5 pixels had intensity of 0. And similarly, you can count 1. I think that's 6. So it's going over here. And similarly, for each bin, you can count the number of times that value is actually occurring in the input image. And that's a very simple histogram. Okay, so that's a basic formulation. And of course, there are like a lot of variations. One variation could be, what if you are not interested in having like too many bins? So in this case, it's showing you like if there are 5 possible values or 6 possible values, then you have 6 different bins. Okay, so 1 bin for each value. You can actually try to club these bins between values. So you can say that, okay, I will only have 1 bin for 0 and 1. Then whenever you see like a value which is either 0 or 1, you will just count into that particular bin. So if you combine these two, then that bin will have almost 11 different numbers. Okay, and in total, then let's say you have only 3 different bins. 1 bin for 0 and 1, second bin for 2 and 3, third bin for 4 and 5. And of course, like this is one extreme, right, where you have 1 bin for each number. The other extreme is, and of course that's not practical, but let's discuss that. The other extreme is when you only have 1 bin, which means that you just have 1 bin and all the values actually goes to that bin. And that will just tell you how many pixels you have. So that's the other extreme. Okay, ideally we want to be like somewhere in the middle where we don't have like a lot of bins and we don't have like too few bins, somewhere in between. And one good practice is to have like equal number of values like for each bin. So they will be kind of equidistant. For example, the earlier example we discussed, we talked about like having 2 values each for each bin. Okay, so that's like a simple concept of histogram, and we will use this concept when we are extracting HOG features. So that's why it's really important to understand this. Okay, so that was a normal bin-based histogram, and this is another example which is kind of showing you histogram, and this is showing you histogram of a real grayscale image. And here you can see that the x-axis is actually showing you the intensity of pixels starting from 0 all the way up to 255, which is kind of pure white, and 0 is pure black. And again, the y-axis is just counting number of pixels you have of that particular tone or that particular color. So this is just giving you can say like intensity profile as well. And you can see that it's kind of telling you, okay, you have a lot of pixels which are of this shade, and again, too many pixels of this shade over here, right? And again, you have very few pixels which are actually very, very bright, completely bright. And again, this is a histogram. And this is like one extreme where you have 1 bin for each possible pixel value. Now, let's try to understand what histogram of oriented gradients are. And by the name, you can guess that, of course, this is a histogram, and you know what a histogram is. And of course, you are going to use images to create these histograms. And if you just go through these these terms you have in the name, it's saying like oriented, right? And orientation, is like the direction of your edges, and it's talking about gradients. So in a way, you can guess that what you're going to do is, given an image, you're going to find edges, and those edges or those gradients, you will also take the orientation into account, and you are going to create histograms using those gradients. And that's exactly what this algorithm does. Okay, so let's quickly go through like each step we have, and then we'll talk about each step like in more detail. The first step is, given an input image, you will have like for each pixel location, you will have some pixel value, right? So whichever pixel you choose, it will have, if it's an RGB image, it will have 3 different values, right? So what we want to do is, for each of these, such locations, we want to create HOG feature for that pixel. All right, which means that we can actually compute HOG features for all the pixel values. Okay, so basically we have 5 different steps how we can do it for each pixel. So we'll first do for one pixel, and then you can just repeat that for all the pixel locations to get features for the whole image. Okay, so let's try to understand how we can extract for this location. So what we do is, we first again draw this block here. And again, so far you have seen like we use a lot of these blocks, right, when we process images. So you will see like these are throughout the course. So what you do is, you draw some kind of bounding box. You can call this a block as well. So this is like a square window. And again, this was something which was proposed. It should be a square window, but usually you can have like a odd shaped window as well. So it's not like kind of a restriction, but the standard algorithm uses like a square window. So then what you do is, you divide that block into, again, multiple cells. And in this case, we are dividing into 4 different cells. And of course, you can divide into more than that as well. But let's like go through once, and then we'll see like how that affects the final algorithm, like how many cells we are actually dividing this block into. Okay, so first step was drawing the block. Second step was, we divide that block into multiple cells. In this case, it's 2 cross 2. Okay, so this blue region is called block. So try to understand the terminology as well, because we'll use that a lot. The blue block, the blue square is the block, and these smaller ones are cells. Okay, so we have 1 block, and we have 4 cells here. So this is like a 2 cross 2 grid. Okay, now what we do is, for each cell inside this block, we simply compute a orientation histogram. And we'll talk about what orientation histogram is. But you do that for each cell. You will do for this first cell, second cell, third cell, fourth cell independently. Okay, and you just concatenate those histograms together. So you know that histogram is nothing. It's, let's say if you have 10 different bins, so histogram is going to be 10 different numbers, if you think about this, right? Because for each bin, you will have some value. And at the end, if you have to describe that histogram, it's just 10 different values. So in this case, for example, if you are extracting a histogram which has 10 different bins, this cell will have 10 values. Again, this will have 10 values, and same for these two. And you just concatenate those. So at the end, for this whole block, you are going to get 40 different values. Okay, you just concatenate those. And those 40 different values are actually your features for this pixel location. Okay, now the only missing link is, how do we extract this orientation histogram for each cell? All right, so we will come to that. Now, once you have this 40-dimensional feature for this whole block, we perform some kind of normalization. So you can represent that as a vector V. All right, when we combine, like, let's say all 4 histograms. So we try to normalize this. And again, normalization, you know what normalization is, and there are different ways to normalize, and it's up to you, like which technique you want to use. The whole idea is, you don't want like numbers very big and very small. Okay, so one simple way is, you can just divide like all the values in your vector with the Euclidean norm. Okay, so that's one way. You know what Euclidean norm is. So we don't have to discuss a lot about that. The other way could be, you can divide with, let's say, L1 norm. Okay, and again, you know what L1 norm is. So there are different techniques for normalization, and as I said, you can use any of those. And the third option is, and we are discussing these three because the actual work which proposed this, they tried to do ablations on these three variations. Okay, so some of these, one of this is better, one of this is bad. So, but again, we don't have to worry about it. Just try to understand that it's a normalization step. Okay, so the third option, it was a little more complicated, and the intuition was okay, so let me go through the steps first. So first you divide by Euclidean norm, which was like the first option you had. And then what they try to do is, if any value in that vector is greater than 0.2, they will just clip it to 0.2. Okay. So then the idea is, even after normalization, you are performing a second step of normalization. And this is required because you might have some kind of outliers. Okay, if some value is actually too big. So even if you normalize, then still that magnitude will be there, right? So to take care of those outliers, what you do is, if some value is too big, you just clip it. When you don't care if it's 0.3, if it's 0.5, if it's 0.8, you bring all them down to 0.2. Okay, so it's kind of, you can say you're discretizing your values. And once you did that, then you again renormalize. You can just compute Euclidean norm and divide. So it's like a second step. And again, it's just trying to take care of outliers. All right, so I think those were the only steps you need to compute histogram of oriented gradients. And now let's try to understand. So only missing link is how to compute the histogram. We'll talk about that. Now let's take a step back. So if this is your full image, and as I said, it was firstly used for person detection, but of course you can use for anything else as well. So in case of person detection, you had like image something like this, where you have a person. And that was the reason, like the full image you have, it's like a rectangular shape, right? It's not square shape, because humans, we are like, we don't have square shape, right? So that's the only reason. So given the input image, what you do is, you know, like what will be the cell size, the final cell size you will have inside your blocks. Okay, so you just create these grids, and these are your blocks. So that is like first block, again, blue is the second block. And you can see that, you know, again, how many pixels you will have in each block. All right. So each block has 2x2 cells, which is fine, 4 different cells. And size is 8x8. Okay, so each cell is actually 8 pixels high and 8 pixels wide, which means that your block will be 16 pixels by 16 pixels. Okay, and again, those are just numbers. If you have very high resolution images, this might change as well. But in this particular case, let's say these are the stats. And this will be useful because at the end, you will be interested in like, what will be size of your feature, and like how you have to normalize. So for that, you need like these statistics. Okay, so what you do is, you place these blocks at all these possible locations after creating this grid. And for each block, you extract your feature. Okay, and then again, you slide the block. And again, you extract the feature, and you do that like all over again. And at the end, like for each block, you will have some set of features. So what you do is, you just concatenate all those features together, and that will be a very huge feature vector, and that will represent your image. Okay, so that's how it works if you have to extract features using HOG from a big image. But essentially, the core of the algorithm is how to extract features for this one block. If you know that, you can extract features for the whole image as well. You just slide it. Okay. So let's go through the steps for the missing part, which was creating histogram for gradients. So first step is usually like you have an image, you compute gradients, that's in X direction, that's in Y direction. Then you compute the magnitude, you compute like the direction. All this is, I think, we already know that how to compute magnitude, right? And the gradient. Now for each pixel location, now you have the magnitude, you have the gradient. So what you do is, you try to create like a histogram for each cell. Okay, so now for each cell, you have how many? 8 by 8 pixels, right? You have 16 different pixels. And for each pixel location, you will have the gradient magnitude, and you will also have the orientation. Now, what you do is, first of all, let's try to understand how we define bins. It can be a little complicated, but bear with me. So your orientation can go from 0 to 180 degrees, right? Let's ignore the complete 360-degree cycle, because if it's like a vertical edge, it doesn't matter whether it's pointing upwards or downwards, right? It's just an edge in this direction. And similarly, like if it's a horizontal edge, it doesn't matter whether it's pointing towards left or pointing towards right. So let's ignore like that 360-degree view. So we'll have angles from, or you can say orientations from 0 to 180 degrees, right? And what we do is we divide these degrees into 9 different bins. Okay, so orientations from 0 to 20 degree, that's your first bin. 20 to 40, that's the second bin, and so on and so forth. Okay, so each bin has like 20 different orientation values, and that will give you 9 different bins. And if you have 9 different bins, then you know like what your histogram will look like. It will have just 9 values. Okay, one value for each bin. Now let's try to understand how we can construct this histogram for a given cell. Okay, so we are constructing histogram for each cell. So for each cell, you will have 8 by it's 8 cross 8, so it will have 16 different pixel values. And as I said, each pixel value will have a magnitude, gradient magnitude, and an orientation. So what you do is you visit each pixel, you look at like what orientation you have for that pixel location, and then you know that whatever orientation that is, it will fall into one of these bins. Okay. Then you don't just count that into bin. For example, if it's, let's say the orientation is 15 degrees. So you don't just simply say that, okay, for this particular bin, you have 1 pixel. So that was the very, very traditional way. It's slightly complicated than that. So what you do is you do voting, and for voting, you use the gradient magnitude. Okay, because you know that for an edge, like magnitude also plays a very important role. If the magnitude is pretty high, it means it's a strong edge, right? And if the magnitude is low, then it's a weak edge. So we will take that into account, and we use this gradient magnitude to vote, and that vote will go into these bins. Okay, so let's try to understand with one concrete example here. Let's say you have 1 pixel which has let's say orientation of 15. Okay, 15 degrees. And let's say the magnitude was 10. So what will happen is you will see like 15 is actually falling in this particular bin. And right now it's a very, very interesting case, because 15 is like, okay, forget about 15. Let's say the orientation is 10 degrees. Okay, so it's a special case because 10 is exactly at the center of this bin, right? It's 10 degrees away from 0. And it's also 10 degrees away from 20. And 0 and 20 are the boundaries of this bin. So what you do is, if the magnitude of that pixel is, let's say 20, you will just add 20 to this particular bin. All right. And let's say if you have another pixel, again, which has orientation 10 and have magnitude 50, you just add 50 again. Okay, so these are special cases where you are actually having orientation exactly as the center of these bins. But in reality, that won't happen. All right. So therefore, what you do is you distribute these magnitudes between bins. And the way this distribution works is, if the magnitude is at the center, it will just go into that bin because no other bin has share for that. But let's say if the orientation is somewhere in between, and it can go into like either of the 2 bins. Okay, so let's talk about other extreme. The other extreme is, what if you have orientation of 20? Now 20, if you see, like is equidistant from the center of second bin and the first bin, which means this gradient should actually go 50-50 between these two because the distance from the center is actually equal. Okay, so if you have a pixel location where orientation is 20 degrees and its magnitude is 50, so then that magnitude 50 will be divided between those two bins equally. 25 will go into first bin, which is for 10, and 25 will go into the second bin. So you distribute those two. Okay, so those two were extreme cases. Now let's talk like the general case. The general case will be, you might have any kind of orientation. What you will do is you will try to find out the closest two bins which are actually neighboring to that orientation, and you will find out the distance between those centers. And that distance will actually will tell you what should be the distribution of that magnitude. Okay, so extreme case, as we discussed, if it's at the center, it will be 50-50. If it's, let's say, if the distance ratios are 25 and 75, you will distribute like 25% will go into the first, 75% will go to the other. Okay, so it's that simple. It's, if you think about this, this is kind of a weighted average as well. Okay, so what will happen is, and you will use like distance from the other center. For example, if your orientation is at a distance of 15 degrees from one center, and then it will be for sure like 5 degrees from the other center, right? Because the distance between these centers is 20 degrees. So then you will just switch that. So 15 distance will be used for the first bin and 5 will be used for the other bin, because those distances are telling you how close that orientation is to each of those centers. Okay, so that's the idea of distribution. And that's how you construct these like orientation histograms for each cell. So for each cell, now you have these 9 different values. What you can do is you can compute like similar 9 values for other cells. And for each block, you will have 36 different values. And then you can use those 36 different values as features for each block. And of course, you can compute features for all the blocks. Again, concatenate them together. That will give you the full feature vector for the input image. So as I said, it's like a very simple algorithm, but very effective. Okay, so in summary, you have to extract like, first of all, a square window, which is called a block. Okay, then you will divide that block into smaller cells. They could be 2x2 or any other shape as well. Then you compute orientation histogram for each cell. You concatenate like 4 histograms. If you have 2x2, you will have 4 different histograms. And then you will perform normalization, and that's it. That's your HOG histogram algorithm. Okay, so now there are like different set of parameters which actually play a very crucial role how good the features will be. So one of the parameters is how many bins should you use. Okay, so in the example we discussed, we were using 9 different bins, but of course you can use like more bins or fewer bins as well. So you know that your range is from 0 to 180 or it's 0 to 360. So you can create like bins of, let's say, 10 degrees, or it could be 30 degrees or 40 degrees, right? So that's one parameter that will control what should be the size of the histogram, right? And that will control like what will be the size of the feature at the end. So if you're using 9 bins, which is usually the case, then each bin will cover 20 degrees. Cell size, like on the actual image, usually it's used 8x8 pixels. Okay. And block size is usually used 2x2 cells, which means like each block will have 16x16 pixels. Okay, so if you use these configurations, and of course these are like some parameters which can change, but if you use this, then your HOG feature vector will be 36-dimensional long, because for each cell you will have 9 different values coming from the histogram, and you have 4 different cells. So this turns out to be 36. And depending upon like how many blocks you have in your image, just multiply with that number. That will give you the full length of your feature vector. And this is like one visualization of how HOG features actually look like. You can see that it's kind of giving you a good visual, right? What is present, you can say that, okay, this seems like a woman standing here. So this visualization, I think the way it was done is, for each cell, you have the histogram, right? And then you pick like the the orientation which is like more dominant in that cell, and that orientation is actually drawn for that cell, and that's how you get this visualization. Okay, so not exactly HOG histogram, but a way to visualize that. So this will actually help you in debugging like whether your extracted features are meaningful or not. Now the next segment, again, we are going to talk more about features, and we will talk about SIFT features, which are again a very interesting set of features. And this is going to, at a high level, SIFT features includes both your HOG features as well as like the previous and the key point extraction, what we discussed, the corner detection. No, not exactly, but that's like the high level goal, because you're in key points or the corner detection, you are actually trying to detect the key points, right, which are more important. The HOG features, you don't care about key points. You're extracting features from all the possible locations. Now, the idea in SIFT is, what if we don't extract features from all the locations? What if we extract features from only salient regions or key points? And that's why, like, the first part is key point detection. You try to localize which are the important points, and then you extract HOG type features from those locations. Okay. So again, this was like 2004, and it's a very popular paper, and I think last year it was like cited more than 68,000 times, which is a huge number. So citation is something like that many papers have actually referred to this work, which is, I will say, brilliant. Okay. So SIFT actually, the full name is Scale Invariant Feature Transform, and as the name says, these features will be scale invariant, which means that you might have your objects at multiple scales, even then your features are not going to change. Okay, you will still be able to capture them pretty well. And the idea is, okay, so as I said, like these features are first of all invariant to scale. They are also invariant to translation, which means that if you move your object in your input image, still you will extract the same set of features. And they are invariant to rotation, which means that if you rotate your object, still your features will not change, again, which is a very, very powerful feature. And of course, they are invariant to scale, as I said earlier. Okay, so these are some interesting properties of SIFT features. Now, what we do is, given an input image, we try to extract like these local features, which are again based on key point extraction. And I think we have seen this image earlier as well. So the idea is, if you look at the image on the left, so this is a truck, and as a human, we can say that this is a truck. Of course, the orientation of this truck and the truck shown on the right image, it's quite different, right? The orientation is different, the rotation is different, the scale is different. And as a human, we can easily say that these are like almost similar trucks, but for a computer vision algorithm, it's very challenging. Okay, so what SIFT does is, as we discussed, like SIFT is scale invariant, rotation invariant, as well as translation invariant, and we have all those three factors here in these two images. The way it works is, you first try to find out the key points. Okay, and this is just giving like the idea at a conceptual level. So these orange blocks over here, these will be the key points. Okay, so in this left image, the algorithm will detect like these many key points. And one interesting aspect, you can see that the key point, when it's located, you also have the orientation of that key point, because these blocks are not just like vertical or horizontal, right? They are not perfectly placed there. They have some kind of orientation, some kind of rotation. So that property actually helps you in making the algorithm scale invariant, rotation invariant, because then you can handle rotation in your input images. Okay. The second thing is, you can see like these blocks are not like same sized. Okay, so these blocks are pretty small. These are pretty huge. So when we detect these key points, we focus on detecting the orientation. That was the first part. We also focus on the scale of the key point. Okay, for example, this key point, the scale is pretty small as compared to this one. And if we have that factor, then of course the algorithm will have like scale invariance property. Okay, so these are the key points on the left image, again, with the size of the key point as well as the orientation of the key point. And what you do is for each key point, you adjust like the orientation. So you will just rotate it, make it like a normalized orientation. And then you will also like normalize the scale so that all the bounding boxes or all the blocks you have same size. And then you extract those patches, and that's what is being shown here. Okay, so the orientation is aligned, the scale is fixed, and then these are the patches extracted from this image. Right? And similarly, this is like image of the same object, but of course, different orientation, different rotation, and there is some translation as well. So you detect these key points again, and you can see that if you adjust the orientation, adjust the scale, the key idea is you will get similar patch. And if you're extracting similar patches for these two different images, then whatever feature you extract for this particular patch, that feature is going to match. And if that feature is matching, then you will be able to match these two images as well. Okay, so that's the high level idea. And of course, when the algorithm will not be this perfect, there will be some distortion in edges or some distortion in orientations. And one, you can see that you are not actually detecting equal number of key points as well. Okay, in this case, you have 5 different key points. In this one, you have only 3 key points. But still, you will have all those issues. But still, I think it will try to do its job. Okay, so let's try to understand like the full algorithm first, like at a high level. Then we'll try to understand each of these steps in more detail. The first step is you try to perform scale space detection. Right, so you first try to detect like those key points, but before doing that, what you try to do, your search space is actually pretty huge. And the idea is you will first of all search over all the possible locations, but while you're searching, you will try to search at different scales, and that's the key. Okay, so you will try to search at multiple scales, and this search process actually makes it scale invariant. Okay, so that's the one important aspect of this algorithm. And once you have that search space, in that search space, you will try to find key points. All right. And again, this key point localization, we have already talked about, I think, Harris corner detection, right? That was a key point detection algorithm. So this step you can just replace with Harris corner detection or any other key point detection algorithm. It doesn't matter. The whole idea is you're interested in finding those key points. Okay, so this is kind of a modular step here. Now, once you have that, then the third important step is how you assign the orientation. Okay, so for each key point, we also need what's the orientation of this key point. And once you have, so this will give you orientation because you're searching at multiple scales, that will give you a scale. And of course, this second step is going to give you key points. Then having all this information, then you can adjust like the scale, you can adjust the orientation. And the final part is key point description, which is a feature extraction. And again, this step is kind of modular. You can use any feature extraction algorithm for this step. For example, you can directly use HOG, which we just discussed like in the previous segment. All right. So these two parts are like kind of, you can use whatever you want, but the others are important, but this is like the full process. All right. So let's now try to understand the search in multiple scales. And this is actually quite interesting. We'll spend some time on this. So let's see how we can actually perform this automatic scale selection. Okay, so one brute force way will be, let's say you have this particular object which you're interested in, and you can see like this is much bigger scale, right? The object appears bigger as compared to this one, but of course this is the same object. Now it's easier for us to say that these are the same objects because we are kind of, our vision system is scale invariant. It's very powerful, right? We can easily take into account that, okay, this is a smaller object and this is a bigger object. And taking that into account, we can say that, okay, these are the same objects. But the computer vision algorithm doesn't know that these scales are actually different. And it will try to match these two without taking that scale into account, and which makes it very, very challenging. All right, so let's see how we can do that automatically in computer vision system as well. Now, if you look into this yellow bounding box here, so this is a very small bounding box, and this is, let's say, is one key point present in this image. Now, if we look at the same key point on the second image on the right, which has a bigger scale, of course, the bounding box will be much bigger. If we have to look into the same amount of pixels, which we're looking into the first image, right? Of course, the number of pixels will be different, but the actual visual content is actually similar when we take a much bigger bounding box. Okay. So now the goal is how we can figure this out that, okay, this box is, if the scale is 1x, the scale should be 3x. All right. So let's try to go over this. So what we do, we do like a brute force mechanism here, but again, try to understand how this can be done automatically. So we take like a bounding box. It's very small. We start with very small bounding box. And we don't care because we don't know what are the scales in these two images. Okay, we just assume, okay, they are different or they are same. We don't care. So we start with a very small bounding box of same size. And we, let's say, try to perform filtering at this location. All right, so this is, let's say, your kernel and some kernel, and you're trying to capture some kind of response. And let's say if the pattern of the kernel matches with the patch at that location, then you should get like a very high response, right? That you know from filtering. So we start with a very small bounding box and we try to capture the response. And what we do, let's say we start with this. So on the on the x-axis, we have the scale, which is kind of giving you the size of the bounding box. And on the y-axis, we have the response from the filtering operation, whether the filter is actually matching with the image patch or not. And that's the white dot over here. And you can see that when we start with this scale on the left image, then we are getting somewhat like a higher response. But in this case, we are getting a smaller response, which could be because this size filter is actually matching very well with this location, but not with this location. And we know the reason because this has a bigger scale, right? It will, of course, not match. Now, what we can do is we can keep increasing the size of this bounding box. And here you can see that, okay, the response is actually improving further, which means the kernel is actually even matching better. And even in this case, the response is actually increasing. Okay, so as we go right, here you can see that, okay, maybe this scale over here, so this is 3.8, right? So some random scale. And this tells you when your kernel size or your bounding box size is 3.8, then whatever kernel you're using, it's actually matching perfectly with that image patch. And that is giving you the highest response. All right, so which means that to be able to detect this particular pattern in your input image, this is the right scale. Okay, 3.8, and that scale is specific to this image. And you can see that as you keep increasing the bounding box, the response is going down because the actual pattern which you're looking for, it will no longer match, right? The visual features are actually changing. And if you look at the second one, you can see that again, you saw like a peak, but at a much higher scale, which means that for this image, this scale, I don't know what this number is, it's actually hidden behind the transcript. So this is, let's say, 10, right? So a scale of 10 actually matches perfectly with this particular image. Now, why this is interesting? Because you're not changing the filter, you're just changing the size of the image patch on which you're applying the filter. And if in these two images, the same filter is actually giving you similar kind of response, or you can say high response at two different scales, then that in a way is telling you what is the scale difference between these two images. Okay, which means that 3.8 like kind of bounding box is equivalent to 10 times of bounding box when placed on this image. So that's giving you the ratio of the scale you have between these two images. So of course you can automate this process, right? Once you know that, of course we'll have to aberrate across like multiple scales. And that's the idea which is used when we extract SIFT features. What we try to do is we try to apply these kernels or filters at multiple scales. Okay, so that brings in like the idea of scale invariance into the SIFT features. And visually as a human, you can see that, okay, whatever visual information you have inside this box actually matches perfectly with whatever information you have in this bigger box. All right, so now the question is, what should be like a very useful kernel function, or you can say signature function, which you can use across images? And of course, derivatives play a very important role here. And Gaussian is something which, you know, has been shown like very, very useful in the past. And what we do is we use like the second derivative of Gaussian, which if you remember, like is also Laplacian of Gaussian, this kind of curve, right, which can actually detect interesting patterns in your input image, and it can help you in estimating like the variation in scales between two different images. Okay, so let's try to understand how that works. So this is your first derivative of Gaussian. Again, if you compute derivative of this, you will get Laplacian of Gaussian, and you know that looks like an inverted hat. I think we have discussed a lot about that. And that inverted hat, inverted Mexican hat, will look something like this. Now, if you look at this filter, this is kind of, if you try to visualize, this is kind of a blob structure, right? Whenever you have some kind of like very, very unique thing in your images. So what we can do is, if we say that we are describing our key points in terms of blobs, then we can use this Laplacian of Gaussian to actually detect those blobs in your input images. Okay, and again, blob, this is just one example. You could have like any other pattern as well. But even if we can actually detect these patterns in two different images, it will help you in estimating the scale, right? It doesn't have to be like any unique pattern. It's up to you, like what pattern you're trying to match. Okay, so let's try to do that using these blob kind of structures. Now, let's say you have these kind of blobs in your input images, and these are your kernels, which again are Laplacian of a Gaussian. And again, these you are using at different scales. So if you'll have a small blob, something like this, then if this is matching with like the size of this kernel here, you will get a very high response, right? Again, this is just filtering. You are using this as an image patch, and you're using this as a kernel. So you know that if you perform filtering, it's just doing pattern matching. So if you use this kernel, it will give high response for this particular blob because the size is kind of almost similar, right? But this won't give you any response for this bigger blob, because this is like much larger scale. Okay, so everything will be just filtered out. You won't get anything. And this red curve here is showing exactly that. Okay, so as you move from like the small filter on the bottom to the bigger filter on the top, as you're changing the scale, this red plot is actually showing you the response on this kind of input. Okay, so this curve tells you like for this blob, you will get good response for this kernel, but you will get nothing for this bigger kernel, and you will get nothing for this smaller kernel either. Okay, so this is matching with this. And again, if you keep increasing the size of the blob, then you can see that the kernel which will detect this blob is also going to change its scale. And for this bigger blob, you can see that this kernel is going to match with this. So once you know that, why this is interesting, because if you use all these different scaled kernels in your input image, then based on when you're getting higher response, you can actually tell what's the scale of your input image. Okay, if you get high response for this, you know that, okay, the scale is much bigger. If you get a high response for the smaller kernel, you say, okay, the scale seems smaller. And in all this, the kernel is not changing. It's the same kernel. It's just a different scale. The pattern is not changing. It's the same pattern. It's just different scale. Okay, so that's the whole idea about having multiple scales and to be automatically able to detect like what's the scale of your input image. All right, so now what you do is, given an image, right, you use like these multiple scales. These are the same kernels. And this is just showing you like how you change the scale. And this is showing you a standard deviation for that kernel. Right. So if you apply this kernel on this input image, this is the response on the right. Okay. So in a way, what you're doing is you're trying to detect blobs in your input image, or you can say that blobs is a term, but it's trying to detect important or salient regions in your input image. Okay. So this is like one way you can detect interesting points. And you can see, I mean, this is kind of performing edge detection. You know that, I mean, a double derivative actually is a filter used to detect edges, and that's exactly what this is doing. Okay, but let's keep it more generalized and say, okay, these are interesting points. Now you can see that, and again, you have seen this in your first programming assignment. If you change the scale of your kernels, or if you change the standard deviation of your Gaussian filter, then the type of edges you are going to detect that also varies a lot. Okay, so this is exactly showing that. Now, how you extract features from this? Once you have these responses from multiple scales, what you do is you compute like maximum minima across these scales. Okay, so whatever step I'm going to explain, you will do that for all the pixel locations in all these scales. Okay, if you have 5 different scales, you will perform that operation for all the pixels in these scales. Okay, so let's talk about that step. So this activation map here, if you represent that as, let's say, using this horizontal 2x2 matrix, and if you're interested in this location, the crossover here. So what we do is we look into the neighborhood, right, which is like the surrounding pixels. You will have 8 different pixel values, right, in this feature map. And you also look into activation map from the next scale. Okay, so it's coming from the next scale. And again, you will compute like these, you will consider these 9 values as neighborhood of this pixel location, and again for the bottom. So for this location, what you do is, if the response is actually maximum among all these neighborhood pixel values, you will just store that as a interesting point. Okay, so and you do that for all the pixel locations in all the scales. So what that will give you is, okay, let's say if this is the maximum among all these green dots, you will store the XY location, right? And you will also store S. S is corresponding to the scale. Okay, so if this is 1, 2, 3, 4th scale, you'll just say, okay, the scale is 4. So now what's happening? This way you will detect what are the key points in your input image. And jointly, you are also saying that, okay, this is the key point, and this is the scale of this key point. All right. Now, LOG filter, I think we have discussed this earlier, how to get Laplacian of Gaussian. You compute second derivative. But there's a very interesting way how you can optimize computation of this Laplacian of Gaussian. So this LOG filter, and you can actually just compute difference of Gaussian. And that is a very good approximation for this Laplacian of Gaussian. And if you compute difference of Gaussian, because you have 2 different Gaussian curves, and you just perform difference between those 2, that will give you this DOG filter, which is called difference of Gaussian. So in this case, it's interesting because you don't have to compute derivative anymore. Because to compute LOG, you have to compute second order derivative, remember? So it will be second order derivative of your Gaussian function, and that's computationally expensive. So if you want to save some cost, this is a very interesting trick. And let's try to understand how a DOG is actually approximation of LOG. And I think then we will end it here. We are almost out of time. Let me cover this this part. Okay, so let's say you have a Gaussian curve, a Gaussian function, which is shown in the green. Okay, so this has like some kind of standard deviation, and so let's say mean is 0, which is fine. Then what you do is you reduce the standard deviation of that Gaussian, and what you will get like this red curve. Again, this is a Gaussian, but with a smaller standard deviation. All right. Now what you do is you just take difference of these 2. You subtract these values. And what you will get is, you will get this blue curve. I mean, I think it's interesting. You can do the math, but this is exactly what you're going to get. Okay, at this location, you can see if you compute the difference, it's this region over here, right? But it's negative because the green one has negative value, so it will go down. Okay, and if you compare this with the inverted hat or inverted Mexican hat, this looks exactly like that. Okay, you have 0, then slightly positive values, then very big negative values. Again, the symmetry of that. So this you can use in place of your Laplacian of Gaussian. It saves like a lot of computation cost. So we are going to like this is the last segment we have for the lectures on features. And last time we were talking about SIFT features, so we'll finish that segment today. And I think that's the last segment for this lecture. So we were talking about, so we went through what is like the overall approach we have for extracting SIFT features and what were all the different characteristics of this kind of feature. So in SIFT, what we do is we try to first identify the key point locations, or you can say like interesting point locations. And to do that, we look into like blob kind of structure. Okay, and to detect these blobs, we have this Laplacian of Gaussian kernel. And again, it's a very basic filtering operation. So during filtering, you just use this kernel and see if this kind of pattern is present in your input image or not. And you say that, okay, that's like the interesting point which you are actually looking for. And you do that at multiple scales. And again, the idea is like if your scale, if the scale of your image is actually varying, then this will make your algorithm scale invariant. Now, this is I will say is the core of SIFT algorithm. And this slide actually tells you exactly how the SIFT features are extracted. Okay, so I think we briefly went over this again. Let me do a quick recap of this. This is your input image. And these are like all the kernels at different scales. And you, as you know, like we discussed last time, this kernel is actually Laplacian of Gaussian, which you can also say like double derivative of Gaussian. And what you do is to define these kernels. So when you're taking the derivative, the Gaussian function you will use, that will have actually different kind of standard deviations. Okay, so you're kind of increasing the standard deviation for a Gaussian function to obtain these kernels. And then again, you perform filtering using these Gaussian kernels on the on the input image. And it's going to detect like, you can say like these are, you can say interesting points, but mostly we are looking edges here. And again, we are detecting that at different scales. Okay, so that's like the initial step. Now the crux is how exactly we determine whether like a pixel location is a key point or not. Okay, so what you do, so whatever step I'm going to explain, you will repeat that step for all the pixels on all these heat maps, which are coming from different scales. Okay, so we'll just discuss one pixel location, but you will repeat that for all the locations. Okay, so let's say we are interested in this scale, which is the 4th scale. So we will take this heat map. And again, this is just showing like you the grid formation, or you can say like grid format for the same heat map. Now, let's say we are looking at this pixel location. What we'll do is we will try to look the activations of the neighboring pixel locations. Okay, so all the green ones. And while we do so, what we do is we look the neighbors which are in the current scale. So exactly this heat map. In addition to that, we also look into like the other scales. Let's say the scale which is greater than this one and the scale which is less than this one. All right, so these two. So these are the pixels, the neighboring pixels, okay, the green ones, and this is coming from 5th scale. So again, what we do, so these are like all the neighbors of this pixel. And similarly, you'll have neighbors for all the pixels in all these 4 or 5 heat maps, right? So for each pixel, you will see if it's the maximum or not, okay, or it's minimum or not. If it's maximum or minimum, you will say that that's your key point and that's what you are interested in. And you will just record like the XY location of that pixel. And you will also record like from which scale it was coming. For example, for this pixel, if it is like, let's say maxima or minima, we'll have XY location for this pixel and we'll have scale as 4. That's the third parameter. And this is like all we need. So similarly, we'll collect like, we will collect all the key points in these different key maps. And then that will be a long list whenever we find like a maximum or minimum. And then you say that, okay, these are your set of key points. So that's how we determine key points in SIFT algorithm. And this was something interesting. Instead of computing double derivative for your filter, what you can do is you can actually approximate that using difference of Gaussian. So we discussed this briefly last time. If you have two Gaussian kernels with different standard deviation, you can actually just subtract those two Gaussians. And that difference is going to give you a function which looks exactly like inverted Mexican hat, which is your Laplacian of Gaussian function. Okay, so you don't have to compute derivatives, which is kind of expensive because you have multiplication operation there. Instead, you just compute difference of Gaussian, which is computationally cheaper than multiplication. All right, so let's see how we can use this difference of Gaussian. Okay, so what you do is you first like blur your image with the Gaussian kernel with a standard deviation of sigma. Okay, so this is like the the pre-processing step. Then you again blur your image with a different Gaussian kernel, which is k times sigma. So k is your scales, like how you are varying the standard deviation of your Gaussian kernels. Okay, and then you simply subtract 2 from 1. Okay, so this is your image, and this is you have smoothened this image using Gaussian kernel, the first Gaussian kernel. And this is like the second Gaussian kernel, which has a slightly bigger standard deviation. That's why it's blurry. You subtract these two, you got this image. And this is exactly like what you will get if you smoothen your image using a Laplacian of Gaussian kernel. Okay, so that's like a very, very interesting approximation. Now, how you can use that when you're computing features for SIFT? You can simply use like multiple scales of Gaussians, right? For example, in this case, you have just sigma and k sigma, but you can have multiple scales. You just keep multiplying with k, which is like the multiplicative factor, and you can compute like smoothened images like these. Okay, so that will be your smoothened image, and then you can just keep subtracting them. Okay, so this is subtracted from this, and again this is subtracted from this. So you keep doing that over multiple scales, and these are your response function, or you can say like response activations after difference of Gaussian, and this will be like a approximation of your Laplacian of Gaussian as well. Okay, so this is like the same step which we discussed right over here. Okay, and then we perform this operation on those heat maps to get the list of key points. But here you will see like you have a different stack as well, and this is called Octave. So in this Octave, you have multiple scales. Now what you do, you like stack multiple octaves on top of each other. And the difference is, in this case, you were changing the size of the kernel, right? The Gaussian kernel. But you do that for different resolution of your images. So in this case, you are reducing the resolution of your image, and you keep doing that. You can have multiple octaves. So now you can see that you are actually making this algorithm scale invariant from 2 points of view, right? So the first is you are actually using your kernel, which has a different standard deviation. So that's taking care of multiple scales. And you're also performing filtering on like differently sized images. Okay, so at 2 level, you're actually taking that into account. And again, you will repeat like the same process for this stack as well. And again, from this, you will try to find out the key points. Okay, so yeah, this is just like trying to visualize the steps I showed you earlier. And you smooth your image, and you get like, again, you smooth from a different standard deviation, you subtract. So you can keep doing that, okay, as you increase your standard deviation. All right. And at the end, you will take these and you will figure out what are the key points. Again, this is the same step. It's nothing new. Okay, so for each pixel location, you're just trying to figure out whether this is maxima or minima. If it is, that will be list of key points. So once you do that, then the result you will get will look something like this. So all the yellow circles over here were actually detected as key points using the filtering operation, which we discussed in the previous slide. Now you might like see one interesting aspect here, right? So these key points have like the scale factor as well, because the radius of the circle which you are plotting, it's actually varying a lot. You have smaller circles, you have bigger circles, right? So that size of the circle is actually representing the scale. So at what scale you are actually detecting this key point. All right. And what may happen is, like, at one location, you might have multiple scales as well. So that key point could be like being detected as key point for varying scales as well. So that's why you can see like it's actually cluttered at this location so you have like all these key points here, right? And you can see you have smaller ones, then you have bigger ones. Okay, so this will be like a long list, of course, because this was done at like multiple scales and multiple kernels. As I said, like 2 different aspects there. Now, once you have these key points, then the next step was, so this was like the second step, right, in your SIFT algorithm. The next step was you will extract some kind of features from those locations. Now let's try to understand how we can do this. And this is going to be somewhat similar to when we're discussing about HOG feature extractor, right? So what you do, let's say this is your key point. Then you will know the scale of that key point. Okay. So what you do, let's zoom into this. You will see something like this, right? Then what's going to happen is, for each pixel location, when you perform filtering, right, then you can compute gradient orientation. Okay, you find gradient in X direction, gradient in Y direction, then you can compute the orientation the same way you did for HOG features. And that way, for each pixel location, you will have some kind of orientation. And what you do is you use that orientation to compute this kind of histogram. Okay, so for each patch, you can do something like this. And then what will happen, you actually keep those orientations which are clearing some kind of threshold. And you will just ignore all the other orientations. Okay, for example, this particular patch, you will have all these pixels, right? And for every pixel, you will have some kind of orientation. So this is just showing histogram of that. And then you can see that multiple pixels are there which have this orientation. This is like, let's say 20 to 29 pin, right? So a lot of pixels have this orientation. Again, a lot of pixels have this orientation over here, which is, I think, around 300. So then these two are the most prominent orientations you have for this particular patch. So you will keep these and you will just ignore all the other orientations. And then the idea is you will say that, okay, at this pixel location or at this key point, you have 2 different orientations. One is this 20 degrees and the other is like 300 degrees. Okay, so one key point can have multiple orientations. So that's how you compute orientation for your key points. Now, once you have the orientation, then the next step is you try to normalize that. Okay, because what will happen if your images are rotated, then we have seen earlier, right? It's very hard to actually compare those two, right? Because the pixel locations will be shifted and the orientations will be different. So to take that into account, what you do is whatever orientation your algorithm has detected for a key point, you use that to normalize all the key point locations. Okay, so the idea there is, let's say you have this key point location and the most dominant orientation, let's say, was in this direction. Okay, so this is showing the histogram for this on the right here. Okay, so this one is the most dominant one. Right, so the bin will look like this. So what you do, you normalize this, mean you make this dominant orientation like pointing towards north. And that's again just one way. You can normalize in any other way, but whatever you do, you should do that consistently for all the key point locations. So in this case, I will show you how you can normalize everything towards the north. So in this case, what will happen if you shift towards north, then you know this angle, right? Let's say this is 45 degrees from the y-axis. So you will shift all the orientations towards 45 degrees towards left. Okay, that's how you normalize. You can see like all the orientations you have at this patch location, you're just rotating them with this angle. So the idea is whatever the most dominant orientation you have, that will always point towards north. And again, this histogram is just shifting because your orientations will change. But of course, like this is going to be your most dominant one. And after your adjustment or after your normalization, always like this first pin will have the maximum value because that's what you are trying to do. Okay, so that's how you normalize your orientation. And once you have normalized, then it's the same HOG like based algorithm where you try to compute local features in this window around the detection. Okay, so what you do is you have the 16 cross 16 window, which is like 16 pixels by 16 pixels. And then you try to rotate, so you will normalize. And the other factor, you also have scale, right? Different key points will have different scale. So you will take that into account and you will only crop like this 16 cross 16 window based on that scale. For example, if the scale is very big, your patch size will be big, but again, you will have to do some adjustments. You can say like resizing to make it 16 cross 16. So one example could be like if the scale is very small, it could be in that region you don't have 16 cross 16 pixels. Then you'll have to perform some kind of interpolation, or you can say extrapolation, right? To make it 16 cross 16. And then you can just compute gradients, okay, for that window. And again, you can use a smoothing filter or not. So all that is fine. Okay, so this is like the step which is shown here. So each of these bounding boxes is actually showing you key point. And the size of that bounding box is the scale. So if the bounding box is smaller, the scale was smaller. For example, this is like pretty small here, right? And the orientation you have, that is actually the orientation which is dominant in that at that location, at the pixel location. Now what you will do is you will adjust or normalize the orientation. So you will rotate that patch, right? And then you will also resize that patch to 16 cross 16. Let's say if it's, it could be anything else, maybe 30 cross 32 as well. But 16 cross 16 is, let's say, just one example. And again, that's one parameter which we'll have to decide. And you extract that patch. And you can see here that all these patches are 16 cross 16. And for all of those, like the orientation has been fixed. So they are like completely perpendicular. Okay. So now what you do next is for each block, which is 16 cross 16, again, you already have computed those edges, right? You have performed smoothing, so you don't have to do that again. So just reuse those values. And again, for each pixel location, you will have these orientations. Now what you do is you will extract like the HOG kind of features, which we discussed in the previous segment. Okay. And again, this is shown, I think 8 cross 8, but again, that's a parameter. So if it's 16 cross 16 window, you will have 16 cross 16 cells here. Okay. So you similarly break that bigger block into smaller cells, let's say 4 cross 4. And for each cell, which is 4 cross 4, you will have to extract a histogram based on the orientations and depending upon how many bins you have. So in this case, if you have 8 bins, so again, you will divide your 0 to 180 degrees to 8 different bins, or 0 to 360 degree into 8 different bins, and create that histogram. And you will do that for each cell. And in total, you have 4 cross 4, 16 cells. Your feature will be 128 dimension long. Okay. So if you divide that into 4 cross 4, each cell is 4 cross 4, you will have 4 different cells. And for each cell, you will have 8-dimensional histogram. And again, you just concat those like you were doing for HOG feature. That is going to give you 128 dimensional feature vector. So then at the end, what's going to happen is, let's say you have a given image, you detected all these key points, which will be a long list. Then for each key point, you will extract a 128 dimensional feature vector. And depending upon how many key points you have, that will decide like what is the size of your feature vector for that particular image. Okay, so again, this is just a recap of that. This is your 16x16 window, and you are dividing like your window into 4x4 cells, and each cell is 4x4. So what you do is you take each cell, let's say this one, you compute orientation for each pixel location, and then based on all the orientations you have in this cell, you can actually create a histogram. For example, if there are 8 bins, you can have 8 different values for that. And then you will have 8 values for each cell. Then you can just concatenate for all the cells you have in this block. And that's going to give you your SIFT feature descriptor. So again, once you have the descriptor, you can perform all those like post-processing things, for example, normalization and all. So this is again same as HOG. It's nothing new. And again, normalization, you can have different variations, right? So we discussed that you can have L2 norm, you can have L1 norm, or you can do like double normalization. First normalize, maybe clamp higher values, and then again renormalize, right? So all those are different variations, but the whole idea is you just want to normalize your feature vectors. So that was SIFT descriptor, and again, a little complicated than HOG, but if you think about this, it's kind of combining both your corner detection, which has ideas from filtering and edge detection and all, and then combining that with HOG, how you can extract features from your edges. So it is like in a way a complete package, and it gives you very good set of features. And it's still used like today because the features are actually very powerful. And one thing I would like to share is, we are currently actually doing some research on these local features, for example, SIFT. And still today, like after all these years with deep learning research, there are some aspects or some areas where SIFT features are actually much more powerful than the CNN features. Okay, I won't share more about that, but of course, if you're interested, you can come to office hours. I will be happy to talk about it. But it's like ongoing research and like something interesting I wanted to share. Okay, so this is like a quick recap of local descriptors. And so most of these features which we have studied, they are based on histograms, right? HOG was based on histogram. Then even SIFT, we were computing histogram of gradients. And you can have templates as well. So template is something when you are filtering, when you're performing filtering, right? So that in a way, for example, even the Laplacian of Gaussian, that's the template you're actually looking for in an input image. And you can change that template. Okay. So, and then it's combination of these two most of the times. And again, these are just like very common properties which we want to have in these features. They should be robust, they should be distinctive, and of course, they should be compact and as well as efficient. Okay, and so far we have seen like most of these descriptors are actually just focusing on edges or gradient information, which is interesting. But of course, like we can have some descriptors which are maybe only utilizing color information as well, right? For example, if we have some problem where color plays a very important role.